Hello, everyone. Mr. Minix, my name. Math is my game. We're just back from spring break. I'm joined with my first period Algebra 2 class. Wasn't quite the reaction I was expecting, but anyway, here we are in Chapter 8, Section 3. The title of Chapter 8, Section 3 is Rational Functions and Their Graphs. Notice the way there is spelled. If it weren't for all the reading, I'd like to be an English teacher someday. But anyway, rational functions, let's just take a trip down memory lane, what they look like. F of x equals q of, well, actually, let me make it p of x over q of x. What we're saying is a rational function is simply the ratio of two polynomial functions. So we got a polynomial in the numerator and a polynomial in the denominator. Again, taking another trip down memory lane, if you remember what a polynomial looks like, a polynomial is a x to the n plus a whole bunch of stuff plus, and actually I think we said it's a sub n, x to the n plus all the way down to a sub 0. That's what a polynomial looks like. And one interesting thing that's actually going to help with tonight's exercises that this class is going to have is that the exponents on polynomials, all the exponents on polynomials, the reason we use that letter n is because it stands for a type of numbers. Anybody remember what type of numbers n stands for? Ones that aren't synthetic, ones that occur in, thank you, natural. Did you say natural? Good, natural, yeah. So what we're saying is the exponents have to be natural numbers, okay? The exponents have to be natural numbers. So no matter how we put these things together, we might have something like 3x to the fifth minus 4x squared minus 3 all over 2x to the fourth plus 5, okay? We might have something like that. Notice the exponents on the variables are always natural numbers, numbers like 0, 1, 2, 3, 4, 5, etc. So I guess what I'm saying is we're never going to have a fractional exponent. We're never going to have a fractional exponent. So with a rational function, we're not going to have something like 3x to the negative 1. Okay? We're not going to have something like that. 3x to the negative 1, you know, that would be 3 over x. And actually, 3 over x in and of itself would be a rational function. But we're not going to have something like 3x to the negative first over 2x to the fifth. So I guess, I don't know, I guess what I'm saying is there's one question in the homework. It's going to say, are you ever going to be dealing with square root functions? Are you ever going to be dealing with radical functions? Well, what do you think the answer to that is? When do square root functions come up? When you have what kind of exponent? Not a negative exponent, but not an even exponent. I don't know if you remember this. A to the power 1 over n is the nth root of a. So I guess what I'm saying is you're going to have radicals whenever you have a fractional exponent. With natural numbers, does it look like we're ever going to have a fractional exponent? No. Okay. So we're not going to be dealing with any kind of square root functions is the whole point that I want to make here. Okay. So we're kind of off to a rocky start. That's okay. That's what happens. Anybody ever go swimming in Lake Erie at Geneva on the lake? You know when you first step off the beach and you go to get in, you're like, oh, look at all the seaweed. This is nasty. I'm not going swimming in here. And then you step out a little bit further and it's rocky and it cuts your feet real bad. But if you're there on a windy day, there's like 8-foot waves that come in, and that's pretty cool. 8-foot waves on a freshwater lake. Maybe not quite 8 foot, maybe 6-foot waves. So again, let's go back here. F of x is p of x over q of x. One thing that we kind of witnessed last week, actually 2 weeks ago, is the domain of these things. The domain of every single rational function is going to be the same. It's almost all real numbers. It's all real numbers with an exception. It's all real numbers with an exception. Does anybody remember what's not allowed to happen? 0 is not allowed to happen for the denominator. The denominator is not allowed to equal 0. So what we say is the domain's going to be all real numbers except the denominator is not allowed to equal 0. Okay? Because if the denominator is 0, then we have division by 0. So let's just take a quick look at 3 particular rational functions. Let's look at y equals x squared plus 1 over x squared. Actually, I did that inverted. I'm sorry. X squared over x squared plus 1. That's better. That's what I wanted to graph. That actually reminds me of a butterfly. I don't know if anyone ever has caught a butterfly, but it's pretty neat when they land on you. There's one place up in up north you can go and actually butterflies will land right on you. But the graph of this function kind of looks like this. It looks like a butterfly. They had a place at the mall with butterflies the other day? That's cool. That's cool. Sweet. So there's one in particular function. Let's look at a couple more. Let's look at x plus 3. Let's look at x plus 3, x plus 2, and x plus 2. So I'm going to use a green marker to graph the functions in all 3 instances. In these graphs, you'll notice I'm not going to great lengths to make sure the graphs are anything spectacular. But there is something peculiar that happens with that graph, and we'll come back and talk about that in a minute. The last one we're going to graph is kind of what we witnessed last week. What we witnessed last week, something like x plus 4 over x minus 2, x plus 4 over x minus 2. And I'll be honest with you, if some of what we're talking about seems like we're getting into pre-calculus, well, it's because we are getting into pre-calculus concepts. Okay. So we saw some stuff last week that had, or 2 weeks ago, that had branches on it, and it kind of looked like so. Looked like that. So the first graph is weird. It looks like a butterfly. The second one looks like a line with, actually looks like one of those arrows that you put on your head when you play Cowboys and Indians. Do they still play that? Or is that too politically incorrect nowadays? Cowboys and Native Americans? Okay. All right. So anyway, there's a word we need to talk about, and it starts with C. And the word we're going to talk about is continuity. Okay? Continuity. If you just think about what that means, continuity, continuousness. It goes and it doesn't really stop. Do we have any of those 3 graphs that appear to be continuous? All of them? All 3 of them go without stopping at any point? Without having a little hiccup at any point? The one in the front is continuous, you think? It has a stop in it. It has a dip in it. I guess if you chew, you have a dip in it too, right? But that's not really stopping. The function's not really stopping. It never stopped anywhere. So let me define continuity this way. No holes, breaks, or jumps. I didn't mention anything about dips. For a function to be continuous, it can't have a dip in it. And if you do enough dips, then you might get a hole in your mouth, but that's another story. That's leukopelakia, and your health teacher will talk to you about that one. But if we look at this first graph, it does have a dip in. in it, but there's no holes in it, there's no breaks in it, there's no jumps in it. This first graph is what we say continuous. Okay, so let me get out my purple marker here. This first graph is continuous. Okay. The next graph has leukoplakia. It has a hole in it. Well, leukoplakia is not a hole in it, but it's not continuous. Okay, it's not continuous. It has a hole in it, and that hole has a special name, and we're going to talk about that in a minute. The last graph, well, it's not continuous either. Okay, the last graph here, it's not continuous either. Not continuous. And it doesn't necessarily have a hole in it. It has that A word that we talked about 2 weeks ago, an asymptote. Yeah, it has a vertical asymptote, in fact. Okay, so this one has a vertical asymptote. Okay. So if a graph has a vertical asymptote in it, well, then it's not continuous. If a graph has a hole in it, well, then it's not continuous. What are we thinking so far? Make a little bit of sense? At the end of the week, there's going to be some quiz questions over this material. Actually, tonight there's some Math Excel things assigned, and I'll be giving you some print material over this. All right. What's up? Hotheads Burritos is really good. So let's talk about this one for a minute. Removable discontinuity. A removable discontinuity. That is a fancy way of saying a hole in the graph. Okay? And this occurs when there is a common factor. I'm going to put an asterisk by the word factor. When there is a common factor in the numerator and denominator. So a hole, a removable discontinuity, occurs in the graph whenever there is a common factor in the numerator and denominator. So in the homework, in the exercises, there's going to be one set of problems that's going to ask you to determine what type of discontinuities there are. Are there none? Is there a removable discontinuity, such as a hole, or is there some kind of asymptote? And we'll talk about the asymptotes here in a minute. But what I want to do is back up for a minute to the graph in the middle. The graph in the middle, we said, has a hole in it, right? What's the common factor that appears in both the numerator and the denominator? X plus 3. So what we're looking at then is this graph here in the middle. And we're looking at x plus 2 and x plus 2, right? Those are the same factors. Doesn't it seem as though we could cancel those out? If we cancel those out, what the function should look like when we graph it would be a vertical line, not a vertical line, a line with a y-intercept of 3, hey, and a slope of 1, up 1 and over 1. And that's what it looks like, except what? Except there's a hole in it. Where do you reckon that hole happens? Where does it look like that hole happens? When x equals what? When x equals, I heard a 2. If you're a bank, negative 2. Remember what happens, the denominator, in this case, x plus 2, is not allowed to equal 0. So x is not allowed to equal negative 2, and that's the point negative 2 something. Okay? So what we're going to be doing in Chapter 8 quite a bit is setting the denominator not equal to 0. How we feeling? So far, so good. Make a little bit of sense? Okay. Well, before we can go to our first example, we need to talk about where asymptotes occur. Okay. So, vertical asymptotes. Vertical asymptotes. occur when there are no common factors in the numerator and the denominator, and when the denominator equals 0. Okay. Vertical asymptotes occur when there are no common factors in the numerator and denominator, and when the denominator is 0. Now, it is possible for a function to actually have both a whole and an asymptote in it. But in general, vertical asymptotes, if we just think of a real basic rational function, they're going to happen whenever the denominator is equal to 0. That's where they're going to happen. So in a minute, we're going to look at our first example, but we'll back up to those three graphs that we saw a few minutes ago. Okay. So if we back up to those three graphs that we looked at, if we look at the one on the far right, the numerator has a factor of x plus 4 in it. Now, x isn't a factor because it's not x times something, it's x plus something, okay? Some people think you could cancel the x in the numerator with the x in the denominator, and you can't. Let me get my blind out here. A lot of people want to try to cancel this x with this x like that, and you can't do that, okay, because it's not x times something, it's x plus something, okay? So there is no common factor in the numerator and the denominator. Yeah, 4 and 2 have common factors, but it's x plus 4 and x minus 2. Each one of those is an entity. So there's no common factors there. And if we look at the denominator, we say the denominator, x minus 2, is not allowed to equal 0, so x isn't allowed to equal what? X isn't allowed to equal 2, and that's where our vertical asymptote happens in that one, okay? So I guess what we'll do is go to example 1. We'll try to find discontinuities. Example 1, find the discontinuities in each. Example 1, find the discontinuities in each. So there's going to be three parts. Part A, y equals x plus 3 over some things. Y equals x plus 3 over x squared minus 4x plus 3. Now, we're dealing with polynomials, and the reason that I jumped from chapter 5 straight to chapter 8 is for good reason. We just finished chapter 5. You should have factoring fresh in your minds, right? And we should be really good at factoring still. So the hidden agenda here that they don't tell you about is, okay, hotshot, what you need to do is you need to go ahead and factor that denominator. They tell you you really need to factor that denominator. So what's that denominator going to factor into? An x and an x, and a minus 1 and a minus 3, huh? Okay, so now let's think about something. Wholes happen when there's common factors in the numerator and denominator. So is this going to have a hole in it? Is this going to have a hole in it? Let's ask ourselves, is there a common factor in the numerator and denominator? X plus 3 is in the numerator. There's nothing common to that in the denominator. So this isn't going to have any holes in it. So there's no holes here. However, there will be asymptotes. There will be a vertical asymptote when x equals what? And when x equals what? When x equals 3, that's one of them. Because remember what happens is x minus 3 is not allowed to equal 0, so x is not allowed to equal 3. And what I'm saying, when it's not allowed to equal that, there's going to be an asymptote there. Because remember, the asymptote is a vertical line the graph gets close to. And the other one is when x equals 1. Good. When x equals 1. Okay? Now, you might think that I'm just making this stuff up. So if you want to, you could verify this. You could go online. What's our resource online that we could use to graph things? Desmos. There we go. Here is our old friend Desmos. A beautiful free graphing calculator. Here we go. So our numerator is, I guess I'll start with a fraction bar. Numerator is x plus 3. The denominator was x squared. Was it minus 4x plus 3? Minus 4x plus 3. And look at the graph. That is a very unusual looking graph. It looks like something you'd see in science class, doesn't it? But can you tell that there's going to be asymptotes there? Right now, no. Well, let's click on the graph and see what happens. Let's click on the graph and let's see, is x ever going to equal 1? It doesn't look like it. Is x ever going to equal 1? Or is x ever going to get to 3? No. Okay. So that graph does in fact have a vertical asymptote when x equals 1 and when x equals 3. Is there a round up there? If you were to zoom out and zoom out and zoom out on our asymptotes, remember asymptotes are lines that the graph gets close to but never touches. Okay? Because of division by 0, the graph can never equal x equals 1 and x equals 3. Okay? How are we doing so far? All right, let's go to the one then here. We're going to look at y equals x minus 5, y equals x minus 5, and x squared plus 1. Now, are there any common factors in the numerator and denominator? I'm seeing people shake their head. No, you're right. So, because there's no common factors top and bottom, there's not going to be any holes. And, well, let's try this denominator not equal to 0 business. X squared plus 1 is not allowed to equal 0, so x squared's not allowed to equal negative 1. If we solve that, aren't we going to get an imaginary number? And imaginary numbers don't really apply to the Cartesian plane, so I guess what's going to happen here, and I should have been a little more clear on this earlier, but there's no values, no real values. I should have said no real values. There's no real values of x that are ever going to make that denominator equal to 0. So this graph actually is continuous. Okay? This graph is continuous. There are no discontinuities because there's no real values for which the denominator would equal 0. Okay? I love continuous graphs. They're the bomb, diggity. They're the cat's meow. The horse's x squared minus 4, y equals x squared minus 3x minus 4 over x squared, or no, over x minus 4. Factor the numerator. So try that. The numerator factors into something. An x and an x and a 1 and a 4. And we want to come up with a minus 3x in the middle, so it's going to be minus on the 4 and plus on the 1. Hey, wait a minute. Holes happen when there's common factors in the numerator and the denominator. So this graph's going to have a hole in it. Where at? There's going to be a hole when x equals 4. Okay. And if you don't believe me, well, let's try Desmond. Now the hole, I honestly have never graphed one of these on Desmond, so I'm not sure what it's going to look like. I honestly don't know on Desmond what it's going to look like. I know on an 83 what it's going to look like, but I don't know about Desmond. So what do we have up top? X squared minus 4x, or minus 3, was it minus 3x? Minus 3x minus 4 over x minus 4. Okay, so if we look at Desmond, I don't see a hole on the graph anywhere. Let me zoom in a little bit. Let me zoom in a little more. I don't see a hole, and there's supposed to be one. What happens if I trace the graph, though? Let me see if I can get to where x equals 4. Oh. Oh. It actually does show up as a hole, doesn't it? Everybody see that? Y'all thought I was lying to you, didn't you? Any questions about finding removable discontinuities? Okay, good. Well, we got 2 more big ideas to get to, and then that's it. So the next big idea we need to get to is finding vertical asymptotes. And we already talked about it, so let's just go right into example 2. Example 2, find vertical asymptotes. Okay, find vertical asymptotes for each of these. Actually, there's only going to be one. X plus 1, y equals x plus 1 over x minus 2 times x minus 3. Find the vertical asymptotes of that graph. Should take about 8 seconds. 7, 6, 5, 4, 3, 2. Am I watching the game tonight? No. So the vertical asymptotes happen on this when x equals what and x equals what? When x equals 2 and when x equals 3. How do we get that? We set the denominator not equal to 0, and that's what our vertical asymptote is. X equals that number. Piece of cake? Maybe we should go ahead and graph that and Desmos one more time. Let's go ahead and try graphing that on Desmos. How cool would it be if Desmos made a calculator? Well, they have like scientific calculators on here too, I think. Oh, you mean if they made a physical calculator? That'd be pretty cool, I guess. So tell where the bottom part of the graph is. Maybe if I zoom out or zoom out. Oh, there it is. Okay. So this is one of those strange looking graphs again, but there are asymptotes. If you were to trace along the graph, you'll notice that x is never going to actually equal 2, and that x is never actually going to equal 3 either. All right so far? We got one last thing to look at, and to look at this last thing, what we need to do is redefine our rational functions. So suppose f of x equals a x to the m over b x to the n. Okay. So what I'm saying is a rational looking at the new leading code. The denominator has a degree of n. The leading is b. And there's a few things that we need to talk about, and this is going to help us find our horizontal asymptotes. Okay? To find horizontal asymptotes. To find horizontal asymptotes. Sometimes there is going to be some, and sometimes there's not going to be some. In the event that the degree of the numerator is greater than the degree of the denominator, degree, in that instance, there's not going to be a horizontal asymptote. Okay, no horizontal asymptote. Okay, if the degree of the numerator is bigger than the degree of the denominator, there's not going to be a horizontal asymptote. All right. What if It's the other way around. What if the denominator has the bigger degree? Well, if that's the case, then there's a horizontal asymptote, and it's real easy to find. If that's the case, the horizontal asymptote happens when y equals 0. If we think about it, y equals 0, isn't that the x-axis in the Cartesian plane? Okay, so that's in effect the x-axis. Okay. In that instance, the horizontal asymptote, we do need to do some calculations to find it. And the calculation is going to take the leading coefficients quotient. We're just going to take the leading coefficients quotient. We're going to take the leading coefficient of the top divided by the leading coefficient of the bottom. And that's it. Examples, and then we'll be done with this. Like I said, this really isn't that bad if you just take notes, read what these things say. Okay? How do you find horizontal asymptotes? Right here. There's 3 instances. Okay? Are there any questions before we move on to see our first example of this? Yeah. Can you go to the bathroom? I don't know if you can, but you may go to the bathroom. Any other questions? And I'm not going to embarrass anyone on YouTube about who's asking to go to the bathroom, although I could, but I won't. Example 3. Find the horizontal asymptotes. Number A. Try to find the asymptote of y equals 2x over x minus 3. This one, they're the same. So let's look back for a second. If the degrees are the same, how do we go about finding the horizontal asymptote? A over b, the quotient of the leading coefficients. So what we're going to do then is say the horizontal asymptote is y equals a over b. What's my a in this case? 2. And what's my b in this case? How do you know it's 1? It's not there. It's there, but it's not. It's that implicit 1, right? So 2 over 1, what does 2 over 1 simplify to be? 2. So the horizontal asymptote is y equals 2. Okay? How are we doing so far? Now, I know that you don't believe me, so let's go back to Desmond. And we'll graph this. 2x over x minus 3. 2x over x minus 3. Check it out. If we were to trace along the graph, the y values, let me zoom out. The y value is 2, 2.2, 2.19. The y value is 1.92. For these to get to. So number B, let's look at y equals x minus 2. The denominator is going to be x squared minus 2x minus 3. So in this instance, it looks like we've got 3. So in this, the denominator is greater, so it's when y equals 0. So the horizontal asymptote here is going to be when y equals 0. Okay, it's the instance where m is less than n according to our claim here. Okay. So in other words, the graph will never touch down on has a horizontal asymptote. If we follow along over here, the graph never touches down over there. Okay? How's everybody doing? All right. Well, we got one more. Let's see. Y equals x squared over 2x minus 5. Y equals x squared over 2 minus 5. 2, So again, going back to our little three-part table, in this case, the numerator has a larger degree. It's going to have a horizontal asymptote. No. This is not going to have a horizontal asymptote. No horizontal asymptote. Okay? And again, one last time, we'll go. So we got x squared over 2x minus 5. X squared, x squared over 2x minus 5. Oh! We do have example 4. One of the photograph. So let's see. X squared plus x minus 12 all over something. X squared minus 4. Now remember the hidden agenda, they don't tell you this, but what they do want you to do is factor this. Because remember, if there's common factors top and bottom, there's going to be what? There's going to be a hole. So let's try to factor the numerator. What's it factor into? X plus 4, x minus 3, right? 4 is good. X plus 4, x minus 3. What about the denominator? What's it? X. Is it going to be an x plus 4 again? How about an x plus 2 and an x minus 2? So it's not. M and N are equal. Is there going to be a horizontal asymptote? Yeah, the horizontal asymptote. Vertical asymptote. Negative 2. Now, as far as graphing that, from this point, it'd be perfectly fine with you using and graphing this. You should be able to kind of expect what the sketch of the graph would look like, though. The graph's not going to go through that point, and it's not going to go through that point, right? But it is going to do some. Exactly? I don't know. Okay? I honestly don't know. That's it. It's been real. It's educational. Any last second shout outs for anybody watching back at home? Will Duvall, the future Mr. Minnick, Barack Obama. Have a nice day.